All right, we're in 2.7 today. This is on page 109 in your textbook. And so what we're going to start looking at, now we've kind of been through linears, and we're going to start seeing basically what different numbers do to different types of graphs, okay? So through this lesson, you should be learning about something called parent functions, which is kind of the base for every different function that we deal with. And then you should be able to describe what happens to the graphs of those functions using different transformations, all right? So I'm not going to write these down, but this is something on page 109. Again, if you can see it a little bit better by getting out your textbook or going to your ebook, I would copy this box down into your notes, okay? So what this is a family of graphs, and this shows the parent function for each function and each different function that we're going to deal with early on in Algebra 2, all right? This first top left box is called a constant function. It's y equals, and it's just a number. This line right here is a horizontal line with zero slope, and it represents y equals 1. Every y coordinate on that line is 1. That's a constant function. The identity function, or the parent function for a linear equation, is this top right box, y equals x. And so what that means is that we have a y-intercept at the origin, 0, 0, and then in this instance, I have no change to the slope. The slope is 1. If you were graphing y equals x, that would be put a point at 0 and go up 1, right 1, or down 1, left 1, and draw your graphs. The book also calls this the identity function, okay? Your parent function for absolute values at the bottom left is this, y equals the absolute value of x. The vertex is at the origin, or at 0, 0, and this is just a standard width for an absolute value graph. Every other absolute value graph we draw is based off of the absolute value parent function. The parent function lets us know what the shape of the graph is, okay? Over here, bottom right, is quadratic functions. This is the parent function for a quadratic, which is y equals x squared. If you notice, there are no changes on these graphs. It's not x squared plus 2. It's not x minus 3 squared or anything like that, okay? The vertex of this parent function for a quadratic is at 0, 0, and that's normal width for a parabola. So when you see a parabola, you know that it's y equals x squared, okay? Or at least that's the parent function, and that's where we go. Let's keep flying. Let's go to page 110, see what we got going on, okay? So this says, identify the type of function represented by each graph based on what you just saw. Well, you know that if it's in the shape of a V, that it's absolute value. So we know right now the parent function for this equation is y equals absolute value of x. Now that's not the equation of that graph, but that's in the same family as absolute value of x. Over here, this would be the constant function. Specifically, this line is y equals 4. It has 0 slope. It's horizontal, all right? But it fits that constant function. Looking at guided practice 1a, this is a parabola. So you know the parent function is y equals x squared. That's not the formula for this parabola specifically, but we know what family it belongs to. And then here's your linear parent function, guided practice 1b. And we could go find the y-intercept. Looks like it's around -3. We could do rise over run to write that, okay? So what happens now is once you understand parent functions, then every number that we add to a function is just shifting that graph, or kind of changing it may change the width, it may make it wider, may make it skinnier, all right? So we're going to jump down to example 2. And now this is called a translation, all right? So in example 2, they give us this, and they say to describe the translation in this graph, y equals the absolute value of x plus 2. Okay, and again, the title of today's is Parent Functions and Transformations. So transformations means what happens to the parent function to give us a specific graph. All right, so it says to describe the translation and then graph the function. All right, so we have two places that things happen. Things can happen with the x. So if it's absolute value, that would happen in the absolute value bars. If it was quadratic, it would happen in parentheses. Linears is the one that the rules don't necessarily, they apply, but they work a little bit differently. But here's what we're looking for. If we have stuff after an absolute value or after the quadratic, if it was quadratic, what this tells us is this graph from the parent function is going to move either up or down. Now, since we have plus 2, you can think of that here as a y-intercept. That's not a 100% deal, but it works for now. This shifts the absolute value of x graph up 2 units. So make note of that. Anything not involved with the x, meaning it's not in the absolute value bars or it's not in parentheses with a quadratic, that's going to move our graph up or down. And it's true to form, meaning plus means up, minus means down. So what we originally have, the parent function, is this graph y equals absolute value of x, which was vertex at the origin. So this graph right here is y equals absolute value of x. Well, if I'm going to draw y equals absolute value of x plus 2, I'm going to move the whole graph up 2 units. So I'm going to move the vertex up 2 units, and I'm going to draw the same exact graph. The width is the same. This graph is y equals absolute value of x plus 2. So that's a translation or sliding the graph up 2. Let's jump down at the bottom of page 110 to example 2a. And it says this, y equals the absolute value of x plus 3. Notice where the plus 3 is and see how it's different than the last problem. This is with the x is what I say. So this does not mean up 3. This change right here is going to be a horizontal change. So up here you see this, that means, hey, we had a vertical change or a vertical shift or a vertical slide. Here, this is going to be a horizontal shift or a horizontal change or a horizontal slide. The one tricky thing about horizontal slides or translations is that it's backwards from what you think. You would think x plus 3 would move everything to the right 3 units, and that is incorrect. So again, the parent function for absolute value is y equals absolute value of x. We've already talked about that. This shift right here that's with the x actually moves the graph left 3 units. Okay? If you struggle with that, put it in your calculator and check the table. But I'm going to go left 3. Now notice we didn't go up or down any. There's no vertical change back here or vertical shift. So I'm going to go left 3. I'm going to put my new vertex, and it's going to be the same width. And this is that graph. This graph is y equals absolute value of x plus 3. And again, this other one was y equals absolute value of x. So that's what's going on. So a horizontal shift kind of happens with the x. The only one that's just a little bit tricky on is linears, and we're not there yet. All right, real quick, without graphing example 2b, it says this, y equals x squared minus 4. Since it's an x squared graph, we know it's a parabola. That's the parent function. This transformation is not happening with the x, or it's not happening with the actual quadratic part. It's happening behind. This would be a shift of down 4 units. So we would take a normal parabola and just shift down. We'd take the vertex down 4 and every other point down 4 and graph. Catch that. That's some important stuff. Here's the nice thing. Those rules hold true for every function that we're going to be doing in Algebra 2. All right, reflection, page 111. Reflection is literally what it means. It flips the graph. All right, so to get a reflection, looking at example 3 now, when we're dealing with reflections, we're just going to put a minus sign out in front of the function. All right, so it says this, describe the reflection. So you've got to be able to describe these and then graph them. So y equals negative x squared. So this right here, a negative in front, flips the graph, okay? And it flips it, all right here over the x-axis, okay? So this flips across x-axis. Well, you're like, well, it flips what? Well, it flips the parent function. So normally, a y equals x squared graph is right there, and we've got a parabola. So that's y equals x squared. If I'm going to show negative x squared, then I'm going to flip this graph. It's still going to have the same vertex. I'm just going to flip it across the y-axis, and this is y equals negative x squared. I mean x-axis, what did I say? Okay? So just flip it right there. That's all a negative does. Now, catch what's going on. Could you have a vertical shift, like these two, and a horizontal shift, and a flip? Absolutely. So we've got to be able to describe the transformation and then make the adjustment. Okay? So look at example 3a. It says this, y equals the opposite of the absolute value of x. Describe the transformation. Hey, that right there means, hey, flip this graph. Flip what graph? The absolute value of x graph. So normally, absolute value of x makes a v, right? There's absolute value of x. If I flip it, my origin stays the same. I just flip the graph upside down. This one down here is y equals the opposite of, or negative, absolute value of x. This top one is y equals absolute value of x. So it's real simple to show those and real simple to see. Understand that we can do all these transformations together. That is a reflection. Notice the linear reflection right here. The slope just becomes -1. Right? Pretty simple. Let's talk about dilation, changing the size. I'm example 4 now. I'm at example 4. Now, dilations to me get a little bit tricky with linears. It's not a big deal. It's basically going to affect the steepness of the graph or how wide the graph is. So we've got this. It says describe the dilation in y equals 4x. Okay? This number in front of the function, if it is bigger than 1, it's going to make it steeper, okay? Or it's going to vertically stretch. Keep that in mind. Vertically stretch. I'm going to put that in parentheses right here, okay? That's not necessarily the terminology for a linear, so we've got to be careful. All right, here's the parent function for linears right here. Just y equals x, right? Just a line right through the origin. You know, slope is up 1 over 1, or down 1, left 1. Y equals x, normal parent function. Now, y equals 4x is just going to be steeper. The y-intercept is still at 0, but to be honest with you, my slope now is what? Rise over run, up 1, 2, 3, 4 over 1, or down 1, 2, 3, 4 over 1. You can see the steepness of this graph right here. It's steeper. That's y equals 4x. The bigger the number, greater than 1, in this instance our slope is, remember we don't have slope in absolute value or in quadratics. This is making my graph steeper, and there it is. There's drawing it and describing the transformation. This is called a dilation. It's making that steeper, okay? Example 4a, y equals 2 times x squared. So what this does now, all right, this vertically stretches the graph. So that's a vertical stretch. Here's what I mean. So if we have a normal x squared graph, so something like that, there's my parabola, pardon the graph, okay? 2x squared is going to make it vertically stretch, or it's going to make it a little skinnier. It's going to come inside of that. So this one inside is y equals 2x squared. One outside is y equals x squared. The bigger the number gets, greater than 1, the skinnier the graph. It's called a vertical stretch. Now, where that gets confusing is if you have a negative in front, don't let it confuse you. It just means flip the graph, okay? So as long as that number is greater than 1 and you understand that a negative just flips, then those rules hold true, all right? Let's look at 4b. Look at absolute value. Y equals absolute value of 1/3 x, right? This makes a vertical compression, or it shrinks the graph. So again, normal absolute value of x graph is right here. Vertex at 0, 0. Draw the V. Absolute value parent function. 1/3 kind of flattens the graph out. So if this is y equals absolute value of x, and we could go get specific and look up points, not necessarily going to do that yet, okay? I just want you to know what's happening. It's going to be a flatter graph. It's like something got sat on it. It's a vertical compression. This graph is y equals absolute value of 1/3 x, okay? It flattens, it compresses, it shrinks. So you got vertical stretches, you got vertical shrinks or compressions. You got steeper, or obviously that could be less steep is how you could call that if this number was a fraction instead of 1. You can flip the graph with a negative sign. We can move a graph right or left. We can move it up or down. And so what we have to be able to do is do it all at once. So let's go to example 5, and I'm wrapping this thing up, okay? So basically it takes this quadratic graph and it wants us to describe the transformations. Now the nice thing in this, they left them all normal width, so I don't have to mess with it. Coach, how'd you know? There's no number in front of x anywhere. So they didn't do any vertical stretching or vertical shrinking, all right? So basically look at these transformations. I got minus signs, meaning our quadratic flipped. These don't have minus signs, so it means it didn't necessarily flip. I've got horizontal changes. That's left 4, that's right 4. That's left 1, that's right 1, that's right 1, minus is right. And then the pluses and the minuses on behind, I've got down, I've got up. So we got a little mix of everything. Well, let's see what happened to the graph. Obviously, this quadratic is flipped. So choices C and D are gone. That thing is flipped. Okay, we have normal width. Now let's find where the vertex is. So I go, looks like left 1, right? Everybody seeing that? And it looks like up 2. Everybody checking that out? So you're looking at that and you're going, man, this is weird. Well, now we need to go back and look at the equation, because it says that the graph of this is translated 5 units to the right and 3 units down. What's the new function? So they don't want us to write the equation of this. They want us to change it. So we got to make sure that we're reading instructions. That's a great example of doing that. Answer what's there. So this is going to go right 5 units. So 1, now notice we're counting by 2. So 1, 2, 3, 4, 5. Right? Again, 1, 2, 3, 4, 5. Puts us right there at 4. If I go down 3 units from where I were, that's 1, 2, 3. That puts me at -1. So I am right 4 and down 1 for my new vertex, which means every point does that. Well, what's going to say right 4? We already eliminated C and D because it didn't have the flip. Well, right 4, remember, is a -4, and -1 is down 1. So my answer choice there ends up being B. All right? We end up with, remember, g of x just means our graph. It's just our function. The opposite of x minus 4 squared minus 1. Everybody good? Everybody all right? Okay, they start here. Look at guided practice 5, just walking through this. There's absolute value of x. Okay? And it says, based on the graph, which equation can be used to describe g of x in terms of f of x? Meaning, how did we go to g of x if we started at f of x? All right, let's look at the transformation. All right, normal width. I'm looking all here and we're good. I got normal width. Let's see what this vertex did. It looks like, and don't draw in your book, but it looks like I went left 3 and up 4. So I got to find the transformations that fit left 3 and up 4. Remember, left 3 is going to be plus 3. So A and B are gone. They say -3. That graph did not move right. And then if I go up 4, remember, plus 4 on the back means up 4. So answer choice C is how we got from f of x to g of x. If you need kind of a summary of everything we've talked about, look at the bottom of page 112. That is all that you need to know, and we're going to be hitting on that a bunch this year. If you have any questions during these notes, please come ask. I'm available to help you on any and all of this stuff at any time. All right, thank you for your attention.